So let's continue with what we had in the nodes. I think we stopped in here. Previously, we talked about the basic implementation for a node class inside another class, which is linked list. Talked about this thing. Yeah, we had this constructor. We assumed we're going to be implementing a double linked list, like each node has a pointer to the next and to its previous. And our double linked list is composed of a front and a back pointer. It doesn't need to be like this, it's just the way this implementation is. You could do it however, right? In some cases, as I'm going to show you today, you might be having a linked list with just one pointer to the front or one pointer to the back. In this case, we have both pointers, to the beginning and to the back, the front and the back. So let's implement these two methods just as an example. Remember, previously we talked about these things. There could be many different operations you could assume to be done on a linked list. It could be push front or pop front or push back or pop back or erase something or erase some nodes or insert some node in the middle, or it could be all these kind of operations. These two are just some samples, probably getting you prepared for what you're going to be doing. Kind of the same idea in the assignment one, and then later on you're going to have a coding question on this part. It could be recursive, it could not be, or you could have both. You could have one recursive and one non-recursive coding question on this part for the midterm exam. Okay. So as usual, I'm not going to be going over C++. You could. It's kind of the same. You know the syntax, but since we are doing in Python and the assignment is in Python and the midterm is in Python, so I'm going to go over this Python tab instead. The push front means you want to push some node to the beginning or to the front of the linked list. Again, it's a double linked list. And pop front means you're going to be removing that node from the beginning of the linked list. So finding it is easy, right? It's just the front one. Unless you don't have a pointer to the front node or to the first node, finding it's easy. But now we should think about how we can handle removing this one. Remember that previously we talked about arrays. If you have an array already full, you want to put something or insert something to its beginning or pop something from its beginning. It's big O of n, and it needs some kind of shifting. That's what I'm going to show you in here. Both operations in here on a linked list, assuming we have a pointer to the front node, which is kind of always all the time. So these two ones now on a linked list, both should be happening in big O of 1, and that's the advantage of having a linked list in these kind of cases at least. Not only is big O of 1, it's big O of 1 because you're going to be working with these links. You're going to be playing with these pointers, right? And you should be careful doing so such that you don't do it in the wrong order, as we're going to talk about it. So let's go over this first one, which is the push front, and assume we have a linked list. By the way, in these images, we have the steps, and then we have the drawings, right? The same thing, you need to kind of do the same kind of drawings in the part A for assignment 1. Probably you have started. Again, this is kind of drawing we do with the steps in here, and we talk about the process. Now, for now, let's assume we want to do the push front process or operation, and at the time we have a double linked list already in place. It means we have, in this example, we have 4 nodes in black, and this one to the left that you see is the linked list, right? So it's front and back. And the front is pointing to the beginning node, the back is pointing to the end node. Okay. Now you want to have a new node noted as NN. Not a good name, but anyways, this NN is a new node being created, or you want to curate it such that it should be pushed to the front. Now it's going to be new first or front node. The beginning one is step number 1. You say NN should be linked list.node. Remember that node was a inner class inside the linked list. By the way, doing this, preferably you should do self.node because you are inside the linked list. But regardless, uh, for now it's just a subtle difference. Both works. So we can accept this one, linked list.node. Data, it should be DATA, so it's a bit of wrong typo in here. DATA, it should be data because the data is what you put as the data inside your linked list. Just a note, it could be any object. It doesn't need to be just one single number. But mostly when we test you in the, let's say, exam, we just assume data is one character or one digit or one number, right? But it could be anything. So the way we create this NN is linked list.node data and self.front. Remember from the previous page, if I get back to that one, for the node, you have this kind of constructor, the data and the next and the previous. These last two are being defaulted to none. So back to here, when we say make a linked list.node with data and self.front, we haven't mentioned anything for the previous. It means that for the next is going to be pointing to self.front at the time. Remember, we haven't yet done the operation of pushing the NN as the front node or the first node, okay? But we haven't passed anything for the previous. It means the previous is still 0 or none, but the next has been assigned in the argument, the value by the argument self.front, right? So we say the NN should be a new linked list node with the data as its data, with it next being pointing to self.front, which at the time is the first black node before the green one being pushed as the new front, and nothing passed as the third argument. Again, we mean that the previous is at the time none. So far so good. We have created the node, and we have even set its next to be pointing to the previous first or the previous front. Step number 2, we say self.front.prev should be NN. We are trying to change the previous of the previous front node, which was initially none, right? You see it in here. It was initially none. But now it should be pointing back to the new front node. So that's why we say self.front.prev should be pointing to the same place as NN. I think it should be clear. It's playing with references, or in terms of C++ pointers. So we say self.front.prev, which was previously none, now should be pointing back to NN. This is step number 2. Now, if you look at this drawing, the other things which need to be fixed is that the self.front at the time is pointing to the previous front. Now, in step number 3, you say that self.front, this green change, again, changes are shown as green. Step number 3 says self.front should be pointing to NN, like this one. And after this, now you see this new drawing. It seems that the node being pointed by NN is the new node, has been pushed as the new front. And everything seems to be okay. These are all those 3 steps all together. Now the question is, does this code works all the time? And these kind of codes, you should be careful with the edge cases. We tested this one by a list which already exists. So we had 4 nodes as the previous state of the linked list, and we pushed this one to be as the new front. What if the edge case happens? One of the edge cases could be, what if we don't have any nodes, like the linked list is empty? Our double linked list is initially empty. What if this happens? So in these kind of cases, let's see if this code works in that case as well. So again, we're going to be thinking about this edge case that we don't have any linked list at the time. Basically, it's empty. The front is known, the back is known. And we're going to be checking if this same code snippet works to be used as the push front, a valid one in here as well. So step number 1 was NN should be getting the value of linked list.node data self.front. self.front is empty or none, so the next becomes none as well. So far, not bad. I can say good even, because we have curated our only node with its data. Next is none, prep is none, both are acceptable. And this is step number one. It seems to be working because we have just this node in here at the time, right? And its next and previous should be none. And step number two was self.front.pref should be an and. Now this one would crash because self.front is none, and you can't say none.pref, right? And these kind of dots after dots after dots, you should be careful not to get lost, and you should be careful not to get the non-exception pointer, right? So we have this kind of exception happening in here. Self.front is none, so you can't say self.front.pref. So step number two would crash. Then step number three, assuming that we could pass that crash. Step number three was self.front should be an and. It works, self.front is pointing to an and. But it's lacking something. Self.back should be pointing to an and as well, right? Because it's going to be our only node being pushed as the first front node, right? So we're going to be left with this state, which is not good because the back has not been assigned to be pointing to the same and as well. Now we had two problems. Step number two crashed. And after step number three, we didn't have back being pointing to an and. So these two could be fixed if we change our code. Remember, our code was simply like this. We had this step number two crashing, and we had one thing missing, which we previously didn't have to do. Previously, we don't have to touch the back, but now you have to touch the back. So what we can do in these kind of cases to have a nicer code is have an if-else case in this step number two. And if it's the case like this, that would be good to go. If it's the case like it's the first node being added, now you should change that one to be, instead of this step, you can change that one to be pointing or referring back to the end. So overall would be like this. Changing the code to just including the edge case is that we say this is the first step, this is the third step, both work, but the second step is going to be a split. If self.front is none, like this edge case, we set the self.back to be an and everything else is good to go, right? But if self.front is not none, then you're going to be doing the same thing you were doing before. It should be understandable, which we did in step number two here, right? So it depends on whether you're going to be pushing this new node as the front of previous linked list, or the previous linked list is empty, and this new node is going to be your first and only node at the time. So based on all this is the polished code. And now if you go over this one, this works all the time. Step number one, step number three work all the time. Step number two, depending on whether self.front is none or not, doing different things, right? Later on, when we talk about sentinels, probably you don't like this kind of coding, although it's good. But anyways, if you don't like to have if-else in between for step number two, later on when we talk about sentinels, and we would define what do we mean by sentinels, you would get rid of this kind of if-else for the second step. But for now, just accept it the way it is, and I think it's nice. Now, talking about the pop front, the second operation we want to talk about. Pop front means removing something from the beginning, like removing or deleting the first node, okay? So what we do in step number one, we check that there is a node. So step number one is checking to see if the linked list is not empty. If it's empty, it's just simply return because there's nothing to be popped or removed, right? Step number two, you make a local pointer to the first node in the list. Like this is needed because later on you want to change the references and at the end remove or actually delete this RM. Okay, so we set an RM as a variable, and we point that one or refer that one to self.front. Again, it's needed because later on you change the pointers. You should have some way to still access this node such that you could say delete this RM. Okay, so this is the step number 2. You set an RM to be pointing to self.front. Step number 3, you no longer need to be pointing to this first node by self.front for the linked list. You should say self.front should be getting the value of self.front.next. Okay? And this is needed because the second node should be our future first node, right? This is step number 3. And the only thing is wrong in here, if you look at the drawing, is the second node's previous is pointing back to the first, let's say previous first node, which should be removed. So the step number 4 is self.front. And remember, self.front at the time is after step number 3. Self.front is pointing to the second node. So self.front.pref should be null. This is, again, the green change you see it in here. We change the second node's previous to be none because second nodes, at the time second node would be soon our first node. Now you will be left with this first node, the previous first node, which has a next pointing to the second node. But who cares about changing the next, because you're going to be removing the RM, and when you remove the RM, all these things would be removed, including its next pointer. So step number 5 is delete the RM. So this makes it clear for the Python runtime that it should be getting rid of this storage or this space for these nodes sooner or later. Okay? So overall, we would have this code. The first step, checking that the self.front is not none, because if it's none, the linked list is already empty. You don't have anything to do, you just return. But if it's not none, you first assign the RM to be pointing to self.front. Then you say self.front should be self.front.next, because the front should be pointing to the previous second. And then self.front.pref should be none. Talked about this one here, right? So again, step number 1, number 2, number 3, number 4. Step number 5, it's you should delete the RM, such that again it's kind of an indication that later on Python would be removing this this first node. Okay, but as usual, we should think that this code always work. And to think about an edge case in here, as opposed to the previous time, an edge case is not if you have no nodes, because if you have no nodes, it's going to be doing nothing, returning, which is correct. The edge case is here is we assume we have this linked list and we deleted or removed this first node or popped its first front. But what if we have just one node? Does it work then as well? So look at it. What if we have just one node? If we have just one node, the condition is wrong because the self.front is not none. You have one node, right? So the step number 1 is okay. We get into the body of the if. Then step number 2 says assign RM to be pointing to or referring to self.front, which is great so far. So step number 2 works as well. Step number 3 says self.front should be self.front.next. And since the node's next is none, basically the self.front.next is none, step number 3 is still correct because it's setting the self.front to be none as well, which is right because we're going to be removing our only node, so self.front should be none. Step number 4, however, says front.pref should be none. Or basically, we had it in the code, right? Self.front.pref. A bit of typoing here as well. Self.front.pref should be none. But this one, as opposed to the previous one, this one crashes Because when you say self.from.pref should be none, self.from is already none. So you can't say, again, the same thing crashes because self.from is none. You can't say none.pref. And it would crash. So we should think about some way like the same thing you saw, like if else for this edge case for this step 4. And as usual, as you see, then we would be left in this state which self.back is still pointing the previous first or the previous only node. And this should be changed. Like step number 4 needs an if else. After that, it would be safe if you set the self.back to be none instead of this for this edge case, then it should be safe to say delete RM. So as you see, we're going to be having this code. And we name it pop front. I think we did the same for the previous function. Yeah, we did name it push front, self and data, right? For the pop front, you don't need to pass data. You just say pop front because it's clear you're going to be removing the first node. You don't need to have a data being passed in, just removing or deleting the first node. So the first step is correct all the time. The second, as usual, and the third one. These all work. Even the fifth one is correct. The fourth step, as we talked about it, if self.front is none, instead of doing this thing which crashes, you set the self.back to be none as well. Otherwise, it means you have more than one node currently in the doubly linked list you have, and then you would set the self.from.pref to be none, the same thing you did in here when you were doing not an edge case like this one. Okay? So again, as you saw, checking the edge cases is important because at the end of the day is going to be giving you this thing instead of just one statement which might crash in the edge case or in the overall case, general case. Now, having this in place, everything is good. Now we have the code for push front, we have the code for pop front, but again, sometimes some developers probably don't like this idea to have if else. They like to have a general case. In these kind of cases, we go to sentinel nodes. Having the sentinel node in place helps us get rid of that looking at things specifically like if else cases. We could think more general case. So first of all, what's sentinel nodes? Sentinel nodes are some dummy nodes. It's going to be indicating the front and the back of your linked list. Okay, they don't have any data. You don't need to put anything in their data because they're not the actual regular nodes. They're just the sentinel nodes. One sitting as the front, one sitting as the back sentinel, and the whole purpose is to have things more probably a bit smoother, like in the implementation. My recommendation, like in the interview kind of cases, they're going to be asking you without Sentinel one. So I would say work with that one or do your assignment one using that one because I believe assignment one gives you the option to do either Sentinel or non-Sentinel. But regardless, you could do both of them. Just have a practice, as it might be the question on the midterm could be any one of them, or we might again give you the option to do it with or without Sentinels. So in the case of you have options, I would recommend work with the general case, which is not using Sentinels. But anyways, using Sentinels is like this. You have two dummy nodes. By dummy, I mean you don't look at the data because it's dummy data or no data at all, right? As you see, the front pointer is pointing to the front sentinel. The back pointer or back reference is pointing to the back sentinel. Front sentinel is showing here as the left one, the blue one, the back sentinel has been shown here as the green one or the right one. And at the beginning, the sign that the linked list is empty is that the front next is pointing to the back sentinel and the back sentinel's prev is pointing to the front sentinel. And I think it's it's obvious to say that the next of the back sentinel is always none and the previous of the front sentinel is always none. This is a sign that the linked list is empty. Okay. Now, having said so, the implementation is like this. You're gonna have this constructor for this one is not touched. This is the implementation for the body of the class for the inner class node, right? It's not changed. But this one is changed because previously we set both of these guys to be none, if you remember. But now self.front says I'm going to be referring to a self.node with none. What does it mean? It means that I'm going to be, remember previously I talked about this thing? You can't say linked list dot or you can't say self dot. This is better because of some reasons. But again, we don't need to get into these details. So instead of saying linked list dot node, I'm saying self dot node. And I'm saying self, make a node with none. It means none for the data. Remember that the next and the previous have none as their default values as well. So after this first statement in the constructor, with the case of sentinels, we have a node which doesn't have any data because it's a sentinel, and its next is none and its previous is none. Okay? Assume we have created a front sentinel, and since we don't have the back sentinel yet, we can't assign it. We can assign its next to be pointing to the back sentinel. So initially, we just created a node. Everything is known in that. Then we create the back one, like the back sentinel, and then we say self.back should be pointing to a node which doesn't have any data because it's the back sentinel. Its next is none. We talked about it in here. The next for the back sentinel should be none, obviously. And now its previous could be set to the self.front because we already have created that one in the previous statement, previous step. So for the self.back, we can say more. We can say this is none, but the third argument to that one should be self.front. It means the back sentinel's previous pointer or reference should be pointing to the front sentinel. Now, the only thing which needs to be changed is the next for the front sentinel is still none, which should be pointing to the correct position or place, which is the back sentinel, right? So now you have this self.front.next should be pointing to the same place as the self.back. Okay? Now, it's a bit more complex regarding the constructor, just a bit, but anything after this should be easier compared to what we had in the case of without sentinels. So look at the steps we have in here. For the push front, so we do everything from scratch. The only thing which has changed is that our linked list has two sentinels, right? We're going to be doing push front. For the push front, we say step number one, NN should be linked list.node. Again, you can say, or better to say self.node. Linked list.node data, self.front. It says that the next should be pointing to the self.front, okay? Self.front.next, sorry. So self.front, just don't get lost, please. Self.front.next. Remember that self.front is the front sentinel. So self.front.next is the first node, is the previous first node. Why do I say previous? Because soon the previous first node should be the second node because we're going to be pushing something and then to the front, right? So again, back to here, we pass data. The second argument is self.front.next, means that the next of this NN we are creating should be pointing to the previous next. So far, so good. And the previous should be self.front. Again, self.front is the first or the front sentinel. So we create this NN and we set its next and prev links correctly using this constructor. The only thing, again, which could be changed is a better name for NN, and instead of linked list, probably self is a better idea. So we created the node, but other things need to be changed as well, right? at the time the previous of the second node is pointing back to this self.front, which is the front sentinel, or the next of the front sentinel is pointing to the second node, which should be changed to the new front node because we're pushing this one as the new front node, right? So in step number 2, we say self.front.next.prev should be NN. Self.front brings us to the front sentinel. You say next, you go to the second node. I do the second because it's going to be soon the second node. And then you say the prev, it's this green link in here. Self.front.next.prev should be pointing back to NN instead, as opposed to being referring to the front sentinel, right? Next one. So far again, the only thing which is wrong at the time seems to be this next for the front sentinel, which should be pointing to here. The way you can say that one way is self.front.next should be NN. Self.front.next is this guy. The next of the front sentinel should be pointing to NN. Okay? As you see, this is just playing with these pointers, and you should be careful to do it in the correct order. And after this one, everything seems to be set, and you are good to go. But as usual, we should think about it. Does this thing work all the time? We tried this one on a linked list initially, not empty. What if in the case, as in the case for the non-sentinels, what if we test these statements or these steps on a double linked list, which is having just nothing, basically just like this, like initially empty? What if it's initially empty? Does this code work as well? So to check it, we trace it, right? What if the linked list is already empty? Just have the front sentinel and the back sentinel. The first step says make a node like the self.node or the linked list.node with the data as its data, or your self.front.next as its next, which is good. Because if you say self.front.next means a pointer referring to the back sentinel, it says the next should be pointing to the back sentinel, which is right. And then the previous pointer is being assigned by self.front. Self.front is the front sentinel. So it says the previous or the prev reference for the NN should be pointing to the front sentinel. So the step number 1 is okay. In step number 2, we had this self.front.next.prev should be NN. But look at this. When you say self.front.next.prev should be NN, as you see in here, in this case, yeah, no problem. Seems no problem because we can say self.front, it brings us to the front sentinel. Then we say self.front.next, bring us to the back sentinel, and then we say it's prev. So that's the meaning of self.front.next.prev. Means the prev of the back sentinel should be pointing back to NN, which is nice. This is NN, right? Which is nice. So no problems. Things which should be adjusted. Now we have this next pointer. Right? We have the next pointer of the front sentinel which should be changed. The step we had previously mentioned was self.front.next should be NN. And it works as well. Self.front is the front sentinel. Self.front.next means pointing this one to the new node, and everything is great. You changed everything. Nothing needs to be adjusted. Even in this edge case, everything works. So the conclusion, this code works all the time. Push front on this new double linked list with sentinels and the constructor. We talked about it. This is the push front, the second method after the constructor. You create your node like this. You change the previous of the back sentinel. You change the next of the front sentinel. Everything works. As you see, this is kind of probably cleaner code, we can say, if you don't like the if-else idea in the previous code. But again, I would say that is a general case. If you like to use sentinels and have sentinels, this is the code working all the time in all the edge cases as well. Regarding the pop front, in this new case with sentinels. So first of all, again, we assume we have a general case, we have some nodes, and we want to remove the first one. As usual, you check that the linked list is not empty. And if it's not, this was step number 2. Again, step number 1, check to make sure that the linked list is not empty. Step number 2, you make a pointer to this node. You just mark it not to lose it. Later on, you want to remove or delete this space, right? This is step number 2. Then step number 3, we try to make the front sentinel's next pointer point to the second node. Okay? As the steps in here, we said self.front.next should be NN. Self.front.next should be NN, which is wrong. And I remember I did a pull request, but probably since it's a bit hard to touch the drawings and redo them for the courselet, Kathy hasn't done them yet. So I did a pull request even the previous semesters. It's not been changed, so just to let you know that this step mentioned in here in this drawing is wrong. It doesn't go hand in hand with the drawing. The drawing is okay. We wanna make sure that the front sentinel's next pointer, like this one, points to the second node, because we want to remove this one later on, right? So to guide you, please look at this one instead, the steps we have in here. First one is the first step, step number 1. You check that the self.front.next is not self.back, because if it's the case, it means that the front sentinel is pointing to the back sentinel as its next node, which means overall that the linked list is empty. If it's not the case, if it's the case, you don't do anything. If it's not the case, you get into the if and do these steps. But we were talking about the step number 2, which is this one. RM is self.front.next, right? This was this one. It doesn't have the step mentioned in here, so look at here, the code. RM is self.front.next. And the next one is even wrong, which we say self.front.next should be NN, so cross off this one. The right one is this guy. rm.next.prev should be rm.prev. So look at this. rm.next.prev. Oh, God. Another thing wrong. Look at this one, sorry. Even the order should be changed. So it doesn't matter, but if I like to go step by step using these drawings, you should change these ones as well. So look at this one instead. rm.prev.next should be rm.next. So rm.prev.next, if you follow the links starting from the rm.prev.next means the next for the front sentinel, right? Should be pointing to rm.next. Remember that you could express some of these things easier as well. There is no one right or wrong way. So I'm going to talk about it later on. Just focus on step number 2, which should be rm.prev.next. Should be getting the value of rm.next. rm.prev.next means the next of the front sentinel should be pointing to rm.next, means to the currently second node. The way you could say this one even easier is you could say self.front.next should be pointing to rm.next, right? We didn't need to make this even this complicated. But anyways, this is not wrong, and it's probably some way to tell you that there is more than one way to work with these pointers. Just be careful when we have these kinds of dots after dots. When you say rm.prev.next, you should first make sure rm.prev is not none. If it's none, you can't see that next. In this case, we are sure it is not. because rm.prep is pointing to the front sentinel, so you can say .next. Again, it was easier probably to say instead self.front.next should be pointing to rm.next. Okay. Then the fourth step, which in our instructions is going to be this one, not this one. This step says the previous of the currently second node should be pointing back to the front sentinel because you want to get rid of this first node. We're doing pop front, right? So the way we have done it in code is this one again, don't mix it with this one, is that rm.next.prep should be rm.prep. rm.next.prep, which is this guy, should be rm.prep, pointing back to the front sentinel. And this one could be mentioned as rm.next.prep, should be pointing to self.front, probably easier, right? Again, it's not just one way, because rm.prep is the same as self.front. Just to let you know, there is not one single way to express these things, but this is not wrong. The only thing which is wrong is the steps you have in here. Even in step 4, you have this thing which is wrong, right? Self.front.next.prep should be self.front. Okay, this is wrong. Because if you say self.front.next.prep, let me see by the way. I think this was wrong. This one we didn't have. This one was wrong. But this one, what about this one? Self.front.next.prep should be self.front. This one works. This one works another way. Instead of this is another way. As you see, there are many ways. Check again. Self.front points to the front sentinel. You say next, you already have changed next to be pointing to here. Then you come to here, right? And then you say prev, like this prev link or pointer should be pointing back to the same place as self.front. This works, right? But whatever it is, these things are not giving you these things in here, right? So if you want to look at the code, just look at the code and forget about the steps that have been mentioned in the drawings. But now the question, as usual, is does this code work all the time? What if we have the edge case? Remember the edge case in the case we had no sentinels. The edge case was, what if this is the only node we have and we want to remove this one? Does this give us a final stable state? So doing the same idea in here, what if we have just one node? And in this case, again, these things we have in the drawings, I don't trust them much. Let's look at the code. First of all, step number 1 says if self.front.next is not self.back, which is not the case because we have one node. Self.front.next is not pointing to self.back, so we get into the if. If it is correct, it means that it is another edge case which you have no nodes and you do nothing, so correct. Now, in the case that we have just one node, you get into the if. You set the rm to be self.front.next, so this one is correct. So rm is pointing to self.front.next because you want to keep a pointer to here. Then rm.next.pref should be rm.pref. Let's see if this is some other way of expressing that one. We want to have this next pointer of the front sentinel to be pointing to the back sentinel. In the code, we had it like this, right? In here, we have it as self.front.next should be rm.next, which is right. This is another way of expressing the same thing, right? Self.front.next, remember we talked about it even up above. Should be rm.next. I think this is even nicer. Step number 4, self.front.next.pref should be self.front, although you have something else in your code. But anyways, it works. Self.front.next, because self.front was changed to be here, pointing to the back sentinel. So self.front.next is pointing to the back sentinel after this one. And then you say its pref, like the pref for the back sentinel, should be pointing to the front sentinel, which is self.front, which is good. As you see, this code works all the time. Again, you have two different things: the code and the code you have in the drawings. Some of them right, some of them a few of them wrong. Just be careful. You have different ways to express the same code. Anyways, the code is correct. After the step number 4 you had in here, you could safely say delete the RM. So as you see, in the case of with sentinels, either for the push front or for the pop front, you don't have to have if else in between to make the edge cases separate from the overall general cases. But anyways, both work. I would recommend you to learn both of them, with and without sentinels, both of them. So now these were some piece of knowledge you needed to do the same, kind of the same things, playing with these pointers and references in doing these assignment 1 parts A and B and C. And I think now you have everything which you need to have practice on assignment 1. Now let's go to the next topic, which is kind of the last topic we have for the day, which is stacks and queues. And as you know, they are ADTs, or abstract data types, being built on top of the list implementation. So we don't use the stacks and queues for storage. We use them for to utilize some of the solutions, or to facilitate the ways we want to find some solutions to some specific problems. It's about the ordering. And since it's ordering, they can be implemented on top of the list, because the lists already have orders, right? Like we have the first node or the first element and the second element, so on and so forth. So these are some abstract data types. Probably I don't need to introduce them. It's not the first time you see these things. You had them in the previous courses as well. The stack is the first in, last out, like the phyllo structure. Or you can say the last in, first out, but mostly we call it first in, last out, phyllo. The queues are the FIFO, or first in, first out. And as we talked about the idea, both of these guys, since they are going to be dealing with the ordering of the elements, they could be, at the end of the day, when you implement them, could be implemented on a list implementation, whether a linked list or array. We talk about the advantages versus disadvantages of both of them as well. But just want to mention that these are ADTs, not used for storage. It's used for solving problems. And for both of them, at least in this course, we're going to be using the list implementation as the basis for these implementations, for these two classes, or these two implementations, two containers, collections, data structures. As mentioned in the caution, the idea of front, back, top in the stacks and queues, they have nothing to do with their position as data structure. The user who is using your data structure or container or collection doesn't need to know, if I say front of the queue or the back of the queue, where exactly it is. They don't even need to know what your implementation is. They don't need to know, have you implemented this stack using a linked list or an array? As long as it's a list, it's good to go, right? The operations you typically do with these two data structures is you should be able to add an item, you should be able to remove an item, you should be able to access the next item. This is kind of ordering, right? So in the case of the stack, as you know, for adding the item, we say push. For removing an item from the top, we say pop, and the topmost element is being referred as the top. So you always push the top and pop from the top, and you don't know any other way to access the elements other than the top, right? There could be some other operations as well, like seek, just to getting back what's currently stored as the topmost element without returning it as the pop does. But most of the time, or let's say is empty or is full, these could be some other operations. But the main ones are going to be two operations, push and pop, and one property, top, or it could be implemented as a function like seek. For the case of queue, it could be enqueue, adding an element to the end of the queue, dequeue, removing an element from the front of the queue, and the front, which is the idea of if you look at this one as a property, it's like a property like where is the front of the queue. You can write this one as a function as of like seek or front even, which is returning the value of the frontmost element, or who is the front of the queue at the time, but it's not removing it as the queue does. But again, these first two are the most important ones. The way we know stacks and queues is by pushing and popping or by enqueuing and dequeuing, right? Now, regarding the applications, it's case-based. For example, for the case of, by the way, whenever we do the recursion, as you know, behind the scenes, you are utilizing a stack. That is the same thing that when you are trying to turn your recursive solution to an iterative solution, it's like you should create your own stack and you should utilize your own stack in order to be able to turn your recursive into a non-recursive solution. Because anyways, when you do recursive, behind the scenes there isn't a stack, runtime stack being created for you. Most of the times we use stacks, sometimes we use queues to solve some problems. Some examples are in here. I don't think we're going to be seeing any examples of these things in this course, but anyways, these are just some hints for bracket checking. If you want to check like those solutions, lead code solutions, problems which ask you to check the brackets, whether they match or not, you could be using a stack. For infix to postfix expression, we're going to talk about infix, postfix, prefix, the postfix express calculation. We're going to talk about some of these in the second half of the course when we talked about graphs and trees. But for now, just to let you know that these kind of operations could be done best with the stack as your data structure during your implementation. And one example with queuing here for the breadth first tree traversals. Again, we should wait for this one to happen, and in the second half of the course we're going to talk about trees and traversals in the trees, and we're going to be seeing these BFS kind of search or traversal in the queues later on. Now let's go to the implementation. Regarding the implementation, the same as the talk we had for the list, you have two options. You could do it with a array-like list, or you could do it with a linked list, right? The linked list could be singly or doubly, many variations. The same for the arrays, could be fixed size or dynamically sized. Anyways, the best way for you to implement a stack depends on what you have, how many elements you have. Are you going to have more elements? You're going to have fixed size elements. All these things could determine the way you should implement your stack. And here's a recall in here. Recall the operations we need for the stack are going to be push and pop and initialize, like creating an empty stack, checking for the stack is empty or full, checking for the top, like returning a top value without removing it. This could be the general cases operations you could be doing on top of the stack. So having talked about this introduction for the stacks, let's have a look at the array implementation and then compare that one with the linked list implementation. The best way you can do is you can use these animations. You had seen them before, right? So in here we have these animations. You had them from before as well. Here it's been mentioned as a stack implemented with an array. And then you can come here. Previously we talked about this sorting part. Now here you have the linked list part as well, and you have the stacks and queues part as well. So here is implementation of a stack using an array. You have the C++ code to the right, and you can push, showing you how it's going to be pushing an element to the top of the stack. Let me push again. You can even change the value as well. You can push again. It's a good playground for working with these kind of data structures. Now you do pop, pop. You can also check whether it's empty or it's full. Okay. So as you see, or even call the top to return the topmost value. Okay. As you see, everything is happening in the constant time, big O of 1. You don't see any place which I'm looping through something, right? Just I push and push and push, the top index goes on and on and on. And then I pop and pop and pop, the top index is going to be decreased over and over and over. So back to here, as you see, everything is straightforward. The only thing which might be bad regarding the array implementation is that you don't know how many elements you have. So you have to have a fixed size in the beginning, and then even worse is that when you're going to be exceeding the size or the length of the array, you want to add something, then you need to have this to be doubled, right? And then copy everything from here to there. But this could be amortized compared to all the operations. It could be amortized. Now, having said all things about the array implementation, or array-like implementation of a stack, let's have a look at the linked list implementation, which could be a bit more complex. And by the way, getting back to we talked about the array. This is the stack implemented with an array. Now we want to talk about the stack implemented with a linked list. Regarding the linked list, there are more variations. We could have a linked list like circular singular linked list. By circular singular linked list, we mean that the last node is pointing as its next is pointing to the first node. We call this circular, right? Or it could be a singular linked list, just a linked list which is not doubly linked list, just each node has a pointer to its next node. And it could be, even regarding this, we could have varieties. We could have a linked list which has just the first link, like the first pointer pointing to the first node, or it could have the first and the last links, like the first link pointing to the first node and the last pointer pointing to the last node. There could be many different variations. And in the midterm, we could ask you all these guys. So I think this is a good playground to practice all these things. What happens if I'm implementing a stack using a linked list which is circular and singly? What if it is circular and doubly? What if it is singly and it has just the first node pointing to its first? We have just a first link pointing to the first node. What if it's singly, but we have both pointers to the first and the last node? So as you see, there are many different varieties, and please don't get confused in these ones. Just have a clear image on your mind or draw it on paper and then see what's happening. So I'll go through the instructions first and then get back to you to talk about these same things on the implementation, which makes things much more easier to be understood. So first of all, we say doing the linked list implementation for this stack is, of course, kind of a bit complex, a bit more complex, right, compared to the previous one. But let's just go over some cases. The simplest linked list is a single list. Why bother having a previous pointer for each node? Let's have just one next node for each, next link for each node. If this list was implemented with just one pointer to the first node, then the insertion would be big O1 at the front, big O at the back. Because if you have just one first link to the first node, you don't have the back pointer pointing to the back or the end node at the time, right? So if you want to push something at the back of the list, then you need to have the cost of big O of that. What about the removal? Remember that this is for push. This is for what if we want to push to the front, is big O of 1. What if we want to push at the back, which is big O of n? Considering the fact that we have just one pointer to the first node, and the list is singly, right? What about the pop? Pop is removal process. Removal is big O1 at the front because you already have a pointer to the first node. And if it's going to be removing at the back, it's big O of n. So look at it. If you want to do push and pop at the front, is big O of 1 at the front and big O of 1 at the front. But if you want to do it at the back, is big O of 1 at the back and big O of n at the back and big O of n at the back. It means that if you have just one pointer pointing to the first node for a singly linked list, it would be best to design your linked list such that your stack based on linked list such that you always push to the front. You have the topmost element in the front, which gives you both operations at big O of 1, right? So I'm just continuing with these statements. If we added an end pointer to the, okay, this is the next one. So we concluded the way we can design our stack using a single linked list with just having a pointer at the front of them. It's easy to see that you should have your top at the front. You have big O of 1, the same as the array, as opposed to big O of n if you design to push at the back, pop from the back, right? However, if you add an end pointer to the list, so instead of have just one pointer to the first node, what if we have an end pointer to the last node as well? Then insertion to the back is big O of 1. However, still removing from the back is big O of n. What this thing is telling you, as I'm going to show you, and I'm going to show you in the animation as well, is that even if, when you're using a single linked list for your implementation, even if you have an end pointer or the back pointer to the last node in the linked list, even then, it's not worth it to look at the last node as the topmost element in your stack. Because even though the insertion drops to big O of 1, we want to remove from the back, it's still big O of n, right? Let me show you in here. Let's say I go to the stack implemented with a linked list. We have just this first node, right? And we push, as you see in here. Unfortunately, we don't have the code in here, but I think it's going to be easy to see that everything is happening the big O of 1 or constant time. I push and I pop. Everything is constant, right? However, if you had just one pointer, or let's go this way, let's talk about it this way. I make it a circular singular linked list. In this one, I have a last node. Let's make it now singular. Let's make a singular linked list with both pointers. For now, I think it's easier. Just first and last node, we have both of them. It's still singular linked list. Let's do it like push to the front. Do it once more. No loops you see in the code, and even in the animation, you don't see any loop being happening. Everything happening in constant. All the nodes are being inserted in constant time. I do just one more. Then in here, I insert to the front. I want to implement a stack, right? Since I insert to the front, I remove from the front. And the same thing, constant time, we go at 1. Remove from the front, the same thing. So you see it's working great if you assume the topmost element of your stack is the first node. What if, since we have the last pointer, what if we want to look at the last node as the topmost element. So we should insert at the back. Inserting at the back, as you see, is constant time, right? No loops, no problems. But since you insert at the back and you are implementing or simulating a stack container, since you insert at the back, you should remove from the back, right? Because the backmost node is your front. Now here is the only time, or the first time, at least based on our talk, is the first time we're going to see a loop. You're going to see it in the code and you're going to see it in the animation, because you should first find the previous node before this one, right? So let's insert one more back just to make it more obvious. Probably I can have more nodes just to show you clearer that we're going to have loops. Now we're going to remove from the back, right? I'm going to popping from the top, which is top is the last element in here. Now here, first you should be able to move the last pointer being pointing to the second to last, right? The one before the last, or a second to last. Because of this, to find the second to last node, you need to have a loop, starting all the way from the beginning, going to the second to last node. And this is big O of n. You see, probably it's easier to get it on the animations instead of just reading these lines. So now that we are here, let's talk about this one as well. In the animations, it gives you the opportunity to work with the circular single linked list, which has just a last. So let me make it clear. What do we mean by circular? We have, let's insert to the front again. By circular, we mean this. We mean the next of the node is pointing to the first node. In this case, you have just one node. Let's insert one more. It's going to be more clear. As you've seen here, the next of the last node is pointing to the first node. This is the meaning of circular, singly linked list, right? And now, as you see, so far everything has been smooth and big O1. I just insert the front, like push to the front. Now I should remove from the front. Even though I have just one pointer last pointing to the last node, everything still is done in constant time or big O1. Right? What if I had inserted to the back? Insert the back. Let's insert one more. This insertion or pushing to the back is constant time, as you see. But now, removing from the back, you have to do a loop to find the second to last node. So as you see, kind of regardless of the way you have implemented your linked list, regardless, it's not worth it to look at the last node as your front. It's best if you look at your first node as your front, as you see here. Okay? So continuing with the statements, if we were to insert always at the front, then the most recently added item will always be at the front. This removal happens to be at the front. And since we can't do both quickly with a simple singular linked list, doesn't need to be singularly. Anyways, that is what we need to do. It means that it's not worth it to be looking at the last node as the front node, because as I showed you, regardless of the type of the list, it would give you the big O of n from the back. I showed you in here, stack with a linked list. We have just the first node. I think I showed you. And you can see the same thing if you have a circular linked list with just the last node, or if you have a plain singular linked list with a first and the last, right? In all these cases, I think I showed this one as well, just to verify. Oh, here we didn't have the option. We just had push and pop. We didn't have the option to push at the back or pop from the back or whatever. So you should play with these ones instead to get the idea. So this was the way we did the linked list implementation for the stack and the way you could do it better or more efficient. Now regarding the queue implementation, probably the array one is a bit more complex compared to the stack because you have a front in the queue and you have a back rear in the queue. And you add things to the rear or the back of the queue and you service them or remove them from the front of the queue, right? The idea in the array needs a bit of change compared to what we had in the stack. But let's first start with the linked list, which is simpler compared to its array implementation. So for the queue, we start with the linked list implementation. The idea is to use a linked list as the base implementation for our queue. The simplest linked list, as usual, is a single linked list, right? It says if this linked list was implemented with just a pointer to the first node, the same thing we started for the stack, insertion should be big O of 1 at the list, at the front of the list, big O of 1 at the back of the list. I think it's easy to imagine. We're going to go to the animations as well, but it's easy to imagine. You have a single linked list. You have a pointer just to the front. If you want to insert at the front, is big O of 1 because you already have the front. But if you want to look at the back of the list, insert at the back of the list, it's going to be big O of n. Removal is big O of 1 from the front and big O of 1, big O of n at the back. The same reason. Correct? Because if you want to remove what's at the front, it's easy to find. But if you want to see, I'm going to remove at the back, I should first have a pointer from the beginning. I go all the way to the back and then remove what I have at the back. So as you see in here, if we treat our list or singly linked list, if we treat its front to be like you should do NQ and DQ, right? If you NQ at the front is big O of 1, then you should DQ at the back, which is big O of n. If you NQ at the back is big O of n, then the DQ would be big O of 1. None of them is great because in each of these cases, you're going to be left with one of the operations as big O of n. However, if you add an n pointer to the list so that you can find the last node easier, the insertion to the back would be big O of 1. Removing from the back still big O of n. This means that after saying all these things, if you have a linked list with a pointer just to the beginning, there is no way you can make it both operations big O of 1. But if you have both pointers, one to the beginning, one to the end, and if you look at this one, insertion to the back is big O of 1. Removing from the back is big O of n, but who cares? Because if you add or NQ to the end, you're going to be removing from the front, right? That's how this sentence continues. It says, if you perform NQ by inserting at the front, the oldest item is at the back. The DQ is big O of 1. Okay? But, sorry, the NQ is big O of 1, but the DQ is big O of n. So it's not worth it to look at the front of the list as where you should be NQing things. Because the NQ is big O of 1, but then you have to DQ from the back, which is big O of n anyways. Even if you added an n pointer, it's still big O of n, right? So it's not worth it to be NQing at the back. What about the other case? However, after we have two pointers, one to the front, one to the back, if you enqueue by inserting to the end, that one is big O of 1, right? And then since you add it to the back, it means the oldest item is at the front. So you should remove from the front. DQ happens to be from the front, and that one is big O of 1 as well. Looking at the animation just to make it more clear. Let's first go to the queue implemented with a link implementation with the linked list. And here we have a single linked list, or we have a double linked list. Let's play with these ones. First, single linked list with both pointers. Talked about this one, right? So if you insert at the front, it's constant. I insert one more, or in terms of queues, I enqueue, sorry. Enqueuing one more. And since I'm enqueuing to the front, I should be dequeuing or removing from the back because it's a queue, it's not a stack, right? Now when I want to remove from the back, as you see, I need to have a loop to find the second to last node. So this idea didn't work. Inserting to the front, removing from the back. What if we inserted the back? We already talked about it. I just want to show you that one in the animation as well. This is constant, this is constant. And then you want to remove from the front. So I enqueued at the back and I'm going to dequeue at the front. Now this time, it's going to be done easily because you already have a pointer to the first node. Kind of the same idea for circular single linked list with having a last pointer just pointing to the last node. I insert to the front. As you see, it's constant operation, big O of 1. And since I'm inserting to the front over and over, when I want to remove, I should remove from the back, right? Because it's a queue. But then, as you see, there will be a while involved, which makes it big O of n, which is not good. However, if I insert at the back, as you see, it's big O of 1. Once more. Since I inserted the back, I should remove from the front, right? But the DQ happens from the front, and this is done in constant time because it's circular. Even though you have just the last pointer, since it's circular, the next of the last is the first node. So it's happening in constant time, or big O of 1. The lesson, implementation for the queues using the linked list. Always insert or push at the back, or enqueue at the back, and dequeue or remove from the front. That's the lesson. And if you want to play with that one, you can play with this queue implemented with the linked list as well. This is just giving you the idea to enqueue and dequeue, just that. It's not talking about where to. It's correctly doing the right thing, right? So let's do one more enqueue. Adding to the end, and then it's dequeuing from the beginning. It's constant time. The other thing remained is, what if we want to implement the queue with the array? Here it's, as I told you, it's a bit more complex compared to the stack case. What makes it complex is that you have front and rear, or front and back in the queue, right? So if you want to do it with just one array, as you see, operations become big O of n because they need to be shifting. Let's say you have an array, you want to insert to its beginning or enqueue to its beginning, so you have to shift. Then you want to remove from one of the ends. One of the ends could be big O of n, the other end could be big O of 1. So let's go over these statements. I just want to make sure that you got these ones clearly. we want to implement our queue using an array, okay? To insert a value to the front of the list, we would move all existing values one index higher because you have to shift everything, and this takes time. This takes big O of n. To remove a value, we would move all the values to the element one index lower. Both removal and insertion are big O of n. This is general in the case of the array. So if you want to implement your queue based on an array, the enqueue function would be big O of n, right? Because it's assuming you are performing enqueue at the front. So this enqueue inserting something to the front is big O of n. Removing from the back should be big O of 1. Okay? If you want to do the reverse, because already we have one big O of n which you don't like it. But if you enqueue to the end, so that one is big O of 1. But then you should remove from the front, and then you need shifting downward, right? Which that one is going to be a slow big O of n. So both of these cases, they don't help us, as opposed to the case for the stack, which is a bit more straightforward, implementation of a stack using an array. One trick we could do in here is we can assume our array is circular. So after the last node or the last element in the array, we go back or get back to the first. So make our array seem to be circular. And we can assume that we have a limit to contain the number of the elements. Doing this way, we can handle the problem using two indices, one for pointing to the front, one for pointing to the back, and then having this fixed size and assuming that the array is circular, you can do it much more quickly and you can do it in big O of 1. Let me show you what I mean. So back to our animations, we're going to go to the implementation of the queue with an array. What we mean is that we have two indices, front and the back, initially pointing to the first element. And by enqueue, you just add something to the back and increase the back index. Enqueue one more, enqueue one more, enqueue one more. As you see, I'm enqueuing to the back, right? And you want to dequeue, you just do in the same direction. You read whatever front is pointing to and then increase the front. I can do more and more. As you see, they're moving in one direction. And if I remove all the way that front gets to back, I can't dequeue more because the queue is empty. But I can still enqueue. So back goes forward again and again and again. And one thing I like to show you is that we assume that the array is circular. So after I added the last element to the index 14 in this example, I would be back all the way to the first, right? And I can continue enqueuing over and over because after some point in time, if I reach to here, now front becomes back again, and now this time I can't enqueue more because the queue is full. So not only you should have front equal to back, but also you should check for the number of the nodes. If front is equal to back and you have no elements, so you should keep track of the number of the elements, right? And you have no elements, 0 elements, it means it's empty. If front is equal to back and you have n elements, it means it's full. There's different ways to check for the is full or is empty operations, okay? As you see, with this implementation, you have created your queue based on the array implementation of the list. There is some unused spaces. If you haven't used them, this is one bad thing. The other bad thing, as I told you, is that you have to have fixed number of nodes. You can't have, like in this example, you can't NQ more than 14 elements or 15 elements because we have from 0 to 14. You can't NQ more than 15 elements. There is no way you can do that one. But in the case of linked list, you had the option to, right? These are all the things we can talk about, the stacks and queues, different ways, different implementations, the pros and cons, and just make sure in the exam you don't get confused by questions on how to implement a stack or queue such that we have big O1 operations for the NQ and DQ or push and pop based on either arrays or in the case of the linked list, different varieties of linked list. What if we have just the front? What if we have front and last? What if we have just the last? What if the list is circular? What if the list is singly linked list? What if the linked list is doubly linked? So in all these cases, just be prepared to deduct basically what's going to be the best way to implement such that all the operations are happening in constant time or big O1. Okay, having said all this, the next page, which is the last page in here, is talking about the iterators. And previously we talked about that one, as I told you before. You can totally ignore this page. I would say read it once because you're already familiar with the syntax of C++. It's just utilizing some constructors, some operator overloading, default constructors, all these kinds of things like friends, all blah, 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 such that give you this idea of how to use and implement iterators to be going over the elements on a list, regardless of the fact that the list was implemented using array or linked list. But as I told you, the idea of iterators in Python is a bit different. Probably I'm going to show you later on. You can safely disregard this page. You're not going to be using that one. You don't need that one for the assignment. You don't need that one for the midterm test. It's just for your information how you could do this thing in C++. In Python, I told you it's different and it's much simpler. And basically, you don't need to use that one for your assignment one and for the test. If we have some time later on in future, I'm going to show you how you could use the iterators, like the iterator idea in Python. But you can safely, again, ignore this page. It's not going to be used. Your assignment, it's not going to be the midterm test. And next page starts our talk of tables and hash tables and maps and hash maps, which we're going to talk about this one in the next lecture.